so that looks like about everyone. Welcome to the Chess AI workshop. This lovely union between AI at UCI and the Irvine Chess Club. Although it seems like the chess club has been relegated to that very back table, but you know, that's okay, represent. Alright, powering on. So first of all, I thought I'd give like a brief overview of just the background of AI in relation to... Okay, that's weird. My laptop is out of sync with the screen. Okay, we're good. Yeah, I thought I'd just give a brief background on the history of AI and computing, the advances we made up until now, and go over some strategies and then dive into our own implementation. So first of all, it's easy to understand how the computational complexity of chess is absolutely massive. We're dealing with some major exponential explosions here because at any given state there's an average of about 40 different moves you can make. So the branching factor is 40, and the state space includes up to 10 to the 123rd possible game states. And as many people love to throw around, that's more than the number of atoms in the universe. Professor Hayes loves that one in particular. But anyway, yeah, so it took a long time for our computers to even start to be capable of handling this kind of complexity. Many advances in hardware made this possible, but the first major victory of computer chess was Deep Blue versus Garry Kasparov in 1997. And this is significant because it's the first defeat of an actual reigning world champion in official tournament control settings. So the machine had the same amount of time as Kasparov. It was actually a very important match politically. Kasparov himself got really flustered in the second game and accused the AI of cheating. Of course it was not, but to many this actually brought about a lot of existential dread, people wondering if humans were finally obsolete. Luckily, we persevered for a few years after that. But yeah, one characteristic of Deep Blue originally is it relied on sheer computational power, so it would just blaze through 200 million positions per second and essentially just out-calculate its opponent. One great documentary I would recommend is Game Over, Kasparov and the Machine, if anyone's interested in learning more about that. So from there we get to modern chess computing, and if any of you are interested in, or you play chess casually or at a club level or anything like that, you are probably familiar with the powerhouse engines Stockfish and Komodo. Fun fact, Komodo was actually developed here at UCI, which I learned today. But yeah, if you don't play chess, it's hard to put into context just how dominant these engines are over the average player. The average ELO of a chess player is around 1200, and ELO, if anyone doesn't know, is a way of measuring the likelihood of each player winning in a match. So I believe a 200-point rating advantage represents around a 78% chance to win for the higher rated player. So you can imagine playing against Stockfish at ELO 3300. The best players in the world just will never win. It's just not going to happen. So anyway, since these engines became so strong, chess was considered to be a relatively solved game until, just to build some drama and suspense here, AlphaZero burst onto the scene about 8 months ago actually, developed by Google DeepMind. And it's really hard to put into context how significant this victory is. I thought I'd just talk about it briefly because it's just so insanely interesting to me. But AlphaZero is the first, I guess, non-symbolic AI. Well, not the first, but the first to succeed. So you can see the difference in raw computational power here in that AlphaZero can only evaluate around 80,000 positions a second, whereas Stockfish looking at 700 million. So that's a very significant difference, obviously, but it's really not the most chilling fact, because AlphaZero was trained entirely on self-play. So Stockfish, Komodo, these top engines, they kind of represent the pinnacle of human knowledge of chess. Like, we've programmed everything we know into these games, whereas AlphaZero is just a fresh, clean slate. Basically learned the game by itself, right? And it did this with a combination of reinforcement learning, Monte Carlo tree search. I would actually highly recommend the documentary AlphaGo, which is now on Netflix. I should have put it on the slide. There's also a pretty neat quote by the founder of Google DeepMind down here. Doesn't play like a human, doesn't play like a program, it's something in between. it's really hard to explain just how significant this is, but AlphaZero plays in a way that's not really like a computer, and it's just so incredible that it was able to destroy Sockfish in this set. And they played a longer, I think, 10,000 game set after this, and it still won, I think, 67%. Also worth mentioning, it was undefeated, but these games are very impressive. Here's another quote, just to really iron that in, by a Danish grandmaster. I always wondered how it would be if a superior species landed on Earth and showed us all how to play chess. I feel now I know. And I feel like this really irons in the fact that it played in a way so completely different from what anyone expected, and kind of on a level that humans can't really understand. So it was fun to watch, I guess to say. So that's our overview. Our background gets us to where we are today, I suppose. And I thought I'd go over just, okay, first of all I should mention, we are not making AlphaZero. That will not happen in this workshop. We're going to try our best, but it's not going to get anywhere near that. So don't expect a rating of 3,600 or whatever it's clocking in at. But yeah, here's some, I guess just a high-level overview of some general techniques in chess computing. We're going to do our best to implement a few of these. Here's just a full list, and then I'll dive into specifics. This is kind of just a wall of text, so I'm going to try and blaze through it. If anyone has any questions, feel free to ask. So first of all, the crux of many chess engines is Minimax search, which operates by that principle on the screen, which is the worse your opponent's best reply, the better your move must be. So the idea is just to, I guess, constrain your opponent as best as possible, and it relies on the fact that every chess position is symmetrical. So it's kind of a more efficient Minimax search. If anyone's familiar with that algorithm, we're actually going to be dealing with that a little later. But yeah, it's a more efficient way to utilize that because every position is mirrored, so you try and leverage that fact. That's the core of it. And there's a technique called iterative deepening. And this is actually a little counterintuitive, but also I should mention that if any of you are computer science majors, I'm assuming the bulk of you, a lot of this content overlaps with CS 171, so this might seem familiar. Iterative deepening is, I should have explained. Okay, I skipped over a lot of topics, so I hope everyone's following along. But you can think of chess as a game tree, right? Like we make one move, there's a certain amount of move responses, and it's going to expand in a tree about, a branching factor of 40 nodes. And if you think about it in this tree fashion, then we're searching through different depths of the tree. So when you're writing an engine, you want to be able to search down as many moves ahead as you can, to predict your opponent and make strong moves, right? So with that in mind, iterative deepening doesn't actually go for maximum depth right away. It searches each level and then starts again from the top. And it's a little hard to understand why this might be more efficient, but the main idea is that you can recognize stronger moves at the lower levels and then prioritize them as opposed to potentially weaker paths. And this also works well with something called transposition tables, which is the idea of using a hash table to store your calculation for a position, so you don't have to look it up again. So you might encounter that a lot in your deepening. It's a classic time-space trade-off. So here we have alpha-beta pruning, which can be applied to basically any tree search method used by an engine. The crux of alpha-beta pruning is, well, we mentioned the massive state space of chess earlier, which is 10 to the 123rd power. Just inconceivable to compute, completely intractable, really. But through efficient pruning, we can actually get significant depths. So we don't actually have to search every node in the tree, because some moves just aren't worth checking out. And the really impressive thing about alpha-beta pruning in particular is that it will never influence the outcome of a search. And it's a little hard to understand why at the beginning, but the main assumption this makes is that your opponent is playing optimally. So if you take with the assumption that, like, if you've already found a better move the opponent could be making in a certain stance, you don't need to search the worst ones. Like, you can assume they're going to make that move. And I believe there's a picture. Oh, okay, one more thing to mention is alpha-beta pruning is heavily influenced by move ordering. Because if you have a question?
Yeah, one organizational question, do we actually, is it okay to ask questions?
Yeah.
Then are you going to post the presentation?
Oh, sure, yeah.
And yeah, the last thing, which is the only semantically loaded question, is do we need a heuristic always when we search, right? So like when I search to some depth, do I always search to the end of the game, which would be like unlikely, I guess, right?
Yeah.
Or do I have some like board evaluation function?
Right, yeah, that's one of the later techniques we're going to get to. But yeah, definitely, when you're doing a search, you need to have some way to evaluate board states. So you need a way to actually look at a leaf node, or like the last depth you can see, and gauge whether or not this is a good state for you to be in. So very good question, and yeah, we can totally post the slides. But yeah, in terms of move ordering, it's easy to understand how that would help pruning, because if the best moves you find right at the start, then it's easier to cut off the ones that might not matter. So pruning becomes more efficient if you can find a way to find the best moves first. Yeah, here's a little picture actually, which makes it easier to understand. People with experience or knowledge of how Minimax works will have an easier time getting this, but this is the core of a Minimax algorithm, and alpha-beta pruning is being used in this image. A little counterintuitive that we're assuming it actually searches from right to left. So we're assuming it found this negative 81st, and because you're predicting it's your opponent's turn, you're assuming that they're going to make the best possible decision. So assuming they actually take your bishop, we don't have to worry about all these scenarios where they don't. So you can prune all these, because surely they would make the best move. And then you make your best move, which would maximize that position, and this is a way of selecting what can bring you the best evaluation in the end. But yeah, speaking of ways to find moves in the correct order to facilitate pruning, we have the concept of killer moves. And just intuitively, you can think of this concept as like forcing moves, or something that initiates a sequence. And the general idea is to place strong moves ahead in the search tree. And it's a little difficult to do this. It's harder to do in practice for sure. But in theory, you want to track moves that perform well in the tree over and over again, and then store that they work well, and place those moves first when you're doing your search. So you look at the moves that, historically speaking, in your record of games, have worked well. Powerful captures, or something like that. They're often forcing moves, and one way to find these killer moves is to look at moves that cause pruning. But anyway, this is a very important one. Quiescence search, which is trying to combat something called the horizon effect. If you're into chess programming, you may have heard that before. And if we're searching to a certain depth, the idea is that the end of the sequence, or like a key move, could always be one depth below what we're searching. So it's kind of like you're looking out at the horizon, and the answer you're looking for could just be right around the corner. So no matter how deep you search, you might encounter the horizon effect, and that can kind of just ruin the effectiveness of your search. And how we combat this with quiescence search is you notice when a position is violent or chaotic, like at the end of your search depth, and you extend the search in that case. So if you think of, to use some chess terms, if there's a chain of tactics, then you don't want to stop searching. Like you want to see the combination through the end. So quiescence search will follow this through until the position returns to a quiet state, and then stop searching. So you're trying not to miss any moves. This is an important one. Okay. And lastly, this kind of addresses your question a little bit. It doesn't matter how deep you can search if you can't actually tell when you're better in a situation, right? So static evaluation is very important to actually gauging whether or not you're winning in a certain game state. So there are many techniques to just statically, look at a board state and decide like, oh, white's better, black's better. But some general principles are to reward strong pawn structure, active piece placement, penalize if your king's like out in the open, things like that. So these are just ways to try and look at a board state and decide who's better. But it's worth noting that it gets a lot more complicated in the end game or in the opening. Anyway, that's the last of our techniques. Sorry if I went a little too deep in the detail or just rattled off a little too fast. We can actually get into our implementation now. So briefly, we should first make sure that everyone actually can run our shell. So are we all on this starting point? Does anyone have any questions, bugs? We all good to go? Can I get some confirmation that someone can run? Okay, someone can play. All right, that's good. Wow, yeah, I expected more technical difficulties. Good job, everybody. Okay, so we can just get right into it then. So with the shell, I actually gave you a little more than I expected to. So we were going to make it move randomly first. But it already moves randomly, which is good. You got a freebie. Not very complicated to implement, so we're not missing too much. So if you downloaded the whole repository, the skeleton, you should be able to run it pretty much out of the box. Oh, question. Here, you can turn it back on. We have mentors going around trying to assist anyone else has any difficulties just running the match from the start.
Realistically, with regards to the evaluation function, it's not something that you would touch personally, right? Because you're going to be implementing your own assumptions into how the board state should be evaluated, right?
In a way, yeah, but I mean, there are some things which will never change, right? Like, queens won't always work a certain amount. So you can always loop for all the pieces and just, yeah, that kind of thing. There are some general axioms about, like, you know, a knight on the rim is less useful, so you can apply a matrix. We're actually going to do this a little bit later, which just rewards knights being placed in a good place, that kind of thing. But yeah, you do want to try and not be biased when you're evaluating position. That's true for sure. I figure we might as well wait until everyone's on the same page here.
Faster than they do that.
So it seems like mostly everyone is ready. So we're going to go ahead and just get started with it.
Yeah, that's what it is.
So right off the bat, if you try playing with your opponent,
It's actually
you'll quickly notice that all of their moves are completely random. Okay, yeah, that's very unorthodox. Okay, alright, sure. But anyway, so our agent is not playing very logically right now, and while it's entertaining, it would be nice if we could imbue it with a bit of intelligence. So the first step is making sensible moves. So first of all, make sure you're in the engine function section, because the rest of it is just general chess logic. The bulk of the work has been done for us here. Right off the bat though, there's one change that I forgot to make in the skeleton that you guys all have, so we're going to have to recreate it real quick. The AI still has a choice of what to promote to, but in the interest of simplicity, I think it is best if we just make it default promote to queen whenever a pawn reaches the opponent's side. So just to stop any, preemptively stop any errors here, I think we might as well. There's also a typo, which we get to knock out at the same time. So we're getting some major value here. So if everyone can dive with me into line 331, deep into the chess logic section, we are looking at the logic for promoting a pawn. And we want to just make some brief changes to specify different behavior if the player is black. And black is represented as 1, by the way. 0 is white. Just an implementation detail. Set that. Just because of how complex our base chess shell is, it can be a little overwhelming at once. At the beginning. I know we did just dump like a 700-line Python file on you, so hang in there. But the functions are pretty intuitive. So if the team is 1 and we're in this position where a pawn has reached promotion state, then just set that piece to be a queen. Don't even give them the option. But we do get the option of promoting any piece we want. Oh, in case anyone's wondering why there are so many semicolons in the code, I think I heard one comment. I am a die-hard C-style programmer, so I've kind of littered them throughout. That's just the way it is. You can take them out if you want, it doesn't matter. And while we're here, I'm just going to change that typo real quick. Okay. And that should be the only change we need there. Just to make sure I'm going to pull up the game. By the way, feel free to stop me and ask questions at any point. I'm going to ask from time to time, but it's kind of on you if you want to, if I go too fast or something like that. Just bring it up. Okay. So I would have to reach a promotion state to actually check if that worked. Let me try and let him promote on me. Okay, he's moving randomly. It's not going to work. We'll test it later. It would take too long. All right. So we're going to scroll back to our nice safe engine section real quick. Dealing with massive font size here. Okay. So right here you'll see our computer move function. And this is meant to just kind of do it all. At the end of the function you want to actually make your move, and then you swap the team back to white. So right now we're calling pick move, and that is just picking a move randomly. But one important step I kind of passed over is you have to be able to actually generate all the legal moves. And I was nice enough to provide this function, but it's pretty intuitive to think about. Oh, while we're here, okay. Yeah, everyone direct your eyes to the generate legal moves function. There is a change to be made there. I should make it turn-based rather than just based on detecting that way. And I think that's it there. Yeah, very simple change. So anyway, this function will return every possible move for the player, and we pass in which player at the start, whether it's black or white. So essentially this gives you all the options, all the leaves in the tree for one particular game state. And this is very important because later on we're going to we want to figure out which move is actually the best one to make. So first of all, you need to be able to actually find all the moves. That's kind of our first step. But as we saw, we're not exactly making an intelligent decision with that move list quite yet. So that is our next step. And this takes a bit. Just to quickly present you with another slide. I'm going to jump in. What are we going to do next? I wonder. Game state evaluation. We need to actually look at a board state and decide who's better. Question?
Do we have the parameter to generate legal moves?
Ah, thank you. Thank you so much. I think it's over there too. It would have caught me eventually. I'm glad you didn't let me get hit with an error there.
Brett, you got a question? No, it was essentially the same. I was just going to suggest that we could use the default argument.
Yeah.
We could. Yeah, that would be another way to fix it. A little simpler. I could get on board with that, but I mean it's kind of just an implementation until black team start fine. I think we just passed it up. Yeah, true. Because when we're making a computer move, we're always going to be black. Thanks for catching me there. We're also calling it twice right now, but pick move is it's soon going to be phased out as a function altogether, so you don't need to really worry about this one. But the next step is to actually evaluate a board state. So let me take us there. Okay. So in order to be able to look at something and have our AI understand what's better, we need to make a function called evaluate position. You could also call it, just some kind of heuristic, like evaluation heuristic. But yeah, we're going to start from there. And first of all, this step is fairly important. You need to react in a different way if there is a winner. Because if the game state is already won, then I mean obviously whoever won should have the maximum points value. So this is a way to say if there is no winner. You know what, I'm going to make an effort to make my code a little more Pythonic, just to ease it on you. Sorry. Okay. So that's to start with. If there is a winner of the game, then we're going to have a conditional for if it's white, if it's black. So winner less than 2 is essentially saying if it's white or black, because it is possible for it to be a draw. Question?
Yeah, so in computer move, why do we actually call generate legal moves? Because we don't call self peak move, and
Yeah.
where do we use this move list?
Yeah, it's not very efficient. So the answer to that is it's going to be used at a later step, and I should have removed it from the beginning. But yeah, it's called twice, you're right. That move list does not get used because pick moves will generate it again, or pick move. We'll get to that though. Good question. So back to evaluate position. This means that we actually have a winner that is white or black, not a draw. Otherwise, if it's a draw, you might as well return 0-0, meaning no one has an advantage. And once again, if you remember from the presentation earlier, we are just going to use the fact that chess is symmetrical and return 1 rating, like not negative that based on whether you're black or white. The position does not depend on whose point of view we're looking at, is the idea. So if there is a winner, we want to find out, if there is a winner and it's not a draw, we want to find out if it's white or black. This means it's black. Black wins. And again, the only way you know that is if you actually implemented the underlying logic. So that's just the way it was made. And it is a little funny when you actually play and you see that it feels like the board's reversed and you're playing upside down. And that is a little strange, but at least you get to really connect with your AI as you see them playing random moves. So this just takes care of the initial condition. Drop out. This does take up a lot of space as I'm leaving comments and doing complex if statement, but so now that we've actually detected whether someone has won or lost, the root of an evaluation is kind of just to look at all the pieces on the board and assign them values. So a white piece will be worth, like a white pawn is worth, let's say 10 points, and a black pawn will be worth negative 10 points. So this way you can kind of add up all the pieces that are on the board and decide who's better. This is really the most simple way to look at it, but it's a good place to start. So we can just make a dictionary of value mappings here. So we're going to be looping through our board and looking at all the pieces still on it in a second. But for now, let's just start assigning point values. And anyone who plays chess is probably familiar with the classic point system train of thought, where pawns are going to be worth 10, knights are going to be worth 30, bishops 30, or usually it's thought of as 1, 3, 3, rooks are 5, queens are 9. Has anyone heard about that? Anyone who actually plays? Okay, cool. Thank you, Kushal. My chess club members are representing me here. Okay. So yeah, we're just assigning a quick value mapping. Go through to that. This step is a little bit redundant to think about, but you can choose to think of the king as having a massive point value, just to try and get your AI to actually value a king. It's kind of a hacky way to think of it, to be honest, and I don't think it's entirely necessary, but just for the sake of completeness, I guess. If you're wondering why we have an uppercase and a lowercase version,
Honestly, I can't tell from this angle, but
The lower one's supposed to be lowercase. That's because if you have seen our board state up here in the output, all of White's pieces are represented in uppercase and all of Black's are represented in lowercase. So we just need to account for that down here. So the negative ones will be Black, meaning that if you are Black, you want a higher negative evaluation. You want the lowest evaluation possible. That was just coding it away here. Oops. Okay, so now that we have our value mapping, we can start looking through the board and just tallying up based on the pieces that we can see. So in Python, this becomes very simple. We can just start our evaluation at 0.0, semicolon. For piece in self.board, and we have piece classes defined above if you're interested in delving into that, but it's pretty complex. So for every piece in the board, we want to do something. And a piece in this representation is actually just a square, and we kind of need to check if the piece actually contains something. Because in the board, there will be null squares. So if piece is an easy way to tell that we're actually looking at something and it's not just an empty square. And there, you just do evaluation plus equals your value mapping of string piece. You need to call the toString, otherwise it's just a class, or an object, I should say. Okay. I think, yeah, I'm looking at the more thorough version here, but I think it's really just that simple for us. Right place, Yeah, so our evaluation function is really quite simple at this state. We just have the value mapping, we move through all, and we're just going to return the evaluation once we're done. So this just kind of tallies up, what pieces are on the board, essentially. Now, from there, one thing to bring up is we're going to be programming for quite a while before we actually get to toy with our AI again, because essentially it's a big leap from random movement just to actually making an intelligent move. So just bear with us for a second. But after evaluate position, we need a way to... So if you think about, we're looking at a board state, right? From the perspective of the computer. And we want to tally up which move that we make is best. We want to look at the evaluation at each of those board states in our legal moves. So in order to do that without actually making the moves, we need a way to simulate the moves without actually making them. Essentially, we need an undo function so that we can look down into the game tree and then come back up. So just to lay the foundation for that, once again, we're going to have to leave the safety of our engine function section. So bear with me again. Scroll up to piece. Yeah. Way up to, I can give you a line number in a second. Yeah, class piece. And we're just going to add a new function here. Like someone asked, don't worry that this is commented out, by the way. It should have been deleted to begin with. Okay, so now that we're in the piece class, you're going to add a new function, which is different from the regular move-to function. Just make sure you can do it. Yeah, okay. So like I said, the idea is we want to be able to make moves or simulate them in a way that won't actually affect the game state. It just lets us, look at it and actually tell if it's better without actually affecting the game. So we're going to try and make safe move to, which is essentially the move to function, but not actually creating lasting consequences. And the idea here is we're essentially just going to swap. We're swapping the position. Oh, you need to include. Yeah. We need a position parameter. By the way, just for the sake of everyone knowing moving forward, positions are, if you're familiar with the chess coordinate system, positions are a tuple of the column and the row. So it can be thought of like A4, B5, something like that. So essentially we're taking a position and we are going to be setting our piece at that position to, yeah, okay. So piece at, yeah. So we're moving to that position. So we set the piece at that position to ourselves, first things first. And we are going to set our own position to none. So you're moving yourself away, so obviously the square you just left is always going to be empty. So you set your own position to none, and then you want to actually update your internal position so that the piece knows it's on, A7 or whatever. And that's for the purposes of Pygame actually rendering it in the right square. So it's important to maintain your idea of where you're placed as a piece. So that's safe move 2. And we are returning to safe sim. It's very easy to get lost in this massive single file. Okay, so we have a way to evaluate positions, but we still have a ways to go before we can undo moves, and that's the next step we're going for. So the next, if you remember the move function, which we're calling in our actual computer move, we need a way to do that. It's just a level up. Every piece has its own move to function, which move calls. So safe move, what we're implementing right now, we'll call that safe move to function we just made. Okay, so first we want to grab the piece that is at position 1, and you can do this by accessing our board list. And we're going to put in the index that our piece is at. Now the board's just an array through, I think, 64 values, but obviously the position, the tuple, like 0, 3, isn't a way to index a list. So there are just some helpful functions like position to index, very easy to grasp. Position. Now that we have the piece, we can actually, well, first of all, this check is just to make sure we're actually dealing with the piece. Otherwise, we have some issues with, calling these functions on null values. So that's just an easy check we can throw in right away. From here, we're going to do another check. Essentially, if we're simulating a move safely, we need to do something different if something is captured, right? Because we want to undo a move and something is captured. we need to actually put it back where it used to be. So we need to test that we're not taking something. Self.board, position 2 index, and this is just position 2. So this will tell us if there is a piece at the place we're moving to. If there is, we want to store that. So let's just do the same operation. And now we're going to be calling that piece function we made a little while ago. So if we captured something, we want to return that captured piece. That is going to be useful in the outer function which replaces it. Otherwise, we don't need to worry about that. We're just going to do v1 safe move to position 2 and just return them. So this is the last piece we need to actually, before actually moving into the simulate move part. So we're going to jump into that function next.
Can you go back down?
Sure, yeah, my bad.
Thank you.
I'm noticing this syntax could be, or this structure could be different. It's a little redundant, but onwards and upwards.
Do you think we can close out all the other tabs so we can see just the code?
Yeah. Is that better?
Not really. Yeah, it looks the same.
What are the same column? There's like a distraction from those.
Oh, really?
Okay.
Yeah.
Close the bottom tabs as well.
Enter distraction.
Yeah.
Oh, okay. That's much better. Thank you.
But it doesn't have the line numbers, which is
Okay, that
automatic.
might be.
Which
At least everyone can see better.
it's up to you.
Okay. Well,
Control that.
Well, if it's about font size, you could just increase the font.
yeah. I mean, little do you know, this font's actually quite a deal bigger. We could make it just absolutely massive. Yeah. Is everyone fine without line numbers? This feels like it's not that big a deal. Okay, let's just move on. Thanks though. Distraction. Alright, so the next function we're going to make is what we've been talking about for a while, which is actually simulating a move. And this is going to take the same position 1, position 2 idea. Let's actually simulate enacting the move. Refresh original game state after. Yeah. Okay, so from this point, once again we want to, well actually, I shouldn't say once again, but we're going to try and do a safe move right away. So self.safe move from position 1 to position 2. And we're storing what it returns in that piece. And from here, we can... Okay, so what we're trying to do at this level is just search one depth ahead. So one design option here is to do the evaluation in this part before we undo the move. That seems like a logical thing to do for now, but it's worth noting that once we move into Minimax search, this function might not be used at all. But so right now we've made that safe move and we've stored whatever we potentially took. So now is the proper time to actually evaluate our game state before we undo it right afterwards. So as you can imagine what I'm saying, we are going to be calling that evaluate function. And that doesn't take any params, so from there, okay. So right after we evaluate position, a simple way to undo is to first move our original piece back. I know this gets a little hard to keep track of, but we'll get back to playing our Cheery opponent pretty soon. So you move back the original piece, and then if we actually took something, that's what this represents. The piece was captured, needs to be reset, and we're just going to call self.set piece at position 2, what we just took. And it's important to also update the position so it will render properly. From there we can just return our evaluation. And that was a whole lot of code for this simulate move, which will help us look one level deeper in computer move. So now we can return the good old computer move, and we will be moving using that move list. So first things first, let's just get rid of the move tuple, or get rid of the pick move, I should say, because we are going to be making an intelligent decision now. So we have our move list, and we have a way to.
Hey, Brett, I had a request. Can we move back down for a second?
Yeah.
Where do you want to move
Just where we were last.
to? Okay, where we were last for a second.
Simulate move.
Is that right?
Yeah.
Okay. Are there any other questions, by the way? I haven't been asking that enough. Everyone good? All caught up?
So I'll just be nitpicky about something. Eval is a keyword in Python.
That could cause problems. You're right. Evaluation. Thank you. Good catch. Okay. So if everyone's good, yeah, let's just move forward. Okay. So we've got our full list of available moves, and it makes sense for us to just move through each one of them and act out simulating what they would do. And by the way, if you're wondering what move list actually is, it's a list of tuples which represent move sub 1 is the original position, move sub 2. It's like traditional chess format, like A takes, you know what I mean, like B. Yeah, I'm not explaining it very well, but hopefully everyone understands the idea. It's just position 1, position 2, over and over. So for every move in move list, I guess move tuple is a little more descriptive. We are going to, so because we're black, we want to maximize the lowest evaluation possible. Remember that the black pieces are scored negatively. So we're going to try and find our best evaluation score. Best evaluation. And because we're going to be looking for the minimum, we might as well start that as something very high. Best.
Shouldn't we just set best evaluation to the evaluation of the first move in the list, just to be safe?
That's sensible. Yeah. And actually, I was about to just set best move to that, so we might as well, right? Yeah. In fact, if there are new moves to make, we don't really want to do anything anyway, so we might as well do those right here. So if the length of our move list, I guess, less than 1, that's when we want to return. Might even want to
Well,
raise
it's better
this,
to
actually.
write than not length.
Huh?
Than just more Pythonic to write not length.
Ah. Okay, thank you. I'm slowly converting. I need to take away some semicolons too. So otherwise, let's set our best move to the first index of move list. now that we've guaranteed that there is one. And we can set the best evaluation to self dot simulate move. This would be, oops. Sorry, I'm messing up my style over and over. Just position 1, position 2. That's the first evaluation. And now we can start to move through our move list again. It might be worth noting that this is still going to cover the first element of move list, so it's a little redundant, but it's okay. So let's track the current evaluation that we get from simulating this move for each move in the list. Move tuple sub-0, move tuple sub-1, and if this evaluation is better, meaning less than the best evaluation, then we want to set best move to that move tuple. And it really does flow very simply from that point. So with this logic, we should be making the move that maximizes our score only one depth deep. So just the best move we can make in the absolute short term. So right before we exit, let's actually make the move.
Yeah, I feel it's gonna be like a lot of times, so it's better to write asterisk best move. It will just unfold it.
Asterisks.
Asterisk best move. No, before best move. So it will just unfold it into those two.
One best moves on the entire list.
Oh, that's the entire thing, right?
Isn't it a
Yeah,
tuple?
that's,
No, it's not tough, is it?
It's a list.
Is it a list of 2 elements or?
Oh, it's a tuple.
best
It's a
move
single
is the
tuple.
tuple. So we'll add
It'll pass like both
Correct.
is best move the tuple too?
best move is the tuple, yeah.
Okay, then it'll, okay, yeah.
It'll unwrap it.
Yeah,
Well,
it's
right, Does move have 2 parameters? Arguments, I mean?
Yeah, move
Oh,
has
yeah,
position 1,
That,
position 2.
yeah,
fine,
okay.
Did you work? Okay, cool. It's a good trick.
When we update best move, then we also have to update best evaluation.
Very good catch, this would have done nothing. Thank you. Okay. So this logic makes sense for just maximizing this move. So I think we are probably ready to actually just jump into testing this and see if we've actually made some intelligent things happen.
Would it be possible for you to zoom in a bit?
I don't know if that's.
Oh. I can zoom in a lot.
Okay. So if this is too hard, no problem.
I think it was.
Control plus.
I can up the font, so that'll help
Maybe,
a little bit. Okay. Yeah, I apologize for people in the back. It's a huge disadvantage. 27. Is this a little better?
Yeah.
Okay. Whoops. Okay. So let's actually jump into testing this, and if we're lucky, it should at least start recapturing. We can't just beat it up senselessly. Whoa. Okay, hopefully I didn't just press that too fast. Okay, good. We're not automatically spawning 2 chess keys. Let's try making a move. Okay, I like it. Ooh, aggressive. Yeah, it would appear it's making the first move every time because it can't detect there's any change in the evaluation yet. In a sense, nothing is happening.
I see less epigraphically. The less epigraphically first.
Yeah, you're not gonna be able to see this very well, but we can try. You can see it on your own personal laptops, I'm sure.
I guess. You could set the first move, it sets it to random.
Yeah, that's one solution, but I mean, I don't know if I'd really consider it a solution because, it's not necessarily better, it's more interesting, right? But it would definitely be more fun to play against. Yeah, so as far as playing against a fun AI, we've actually taken a step backwards. It was more interesting when he was flailing randomly.
Let's see if it captures.
Yeah, let's see if it captures. Okay, that's a good sign. He's feisty. Okay, but he doesn't see very far into the future. That's pretty much the exact behavior we should expect.
Can you get it to meet you?
I feel like that would take a long time. I can try.
Uh-oh.
Oh, look at him. Oh, he's destroying me. This is embarrassing. This is a good time to test
Yeah, the green. No.
Oh, wait.
Don't capture the code, it crashes.
I mean, the problems are
Alright.
quite weird, right?
Is it drawn? I think it's drawn.
No, something has just gone terribly wrong.
Stop
Our
moving.
This guy just captured
Wait.
Oh, yeah.
Okay. Okay, I truly do not know what's going on right now.
Kill the process.
So I have a hidden queen somewhere? Oh, multiple. Okay. Wow. Yeah, we are really winning this match. Okay. So there is one hacky solution to that bug. I haven't encountered this before. I believe it's actually a problem with generating all the moves, which I provided for you. So we can go ahead and try and fix that. Unless anyone else has an idea as to why we may have
Is it
stolen
something
this.
about ampersand? It looks like some buggy implementation.
It could have been.
wasn't ampersand, was it?
Well,
I think
yeah, it wasn't, but I think it looks like.
Yeah, it may have thought it was, I guess. That's true. I'm really going to want to err on the side of not debugging the entire chess core, though, the core logic. But if it was, then I mean, we're just going to have to live with it.
Well, we could play without the ampersand.
Yeah. We can test it. But in terms of generate legal moves, I have found that sometimes this will generate moves that do not make any sense for whatever reason. I forget what the... Okay. Yeah, so this is a bit of a hacky solution, so bear with me here, but if you recall in that strange match we just played with our friend, we were making negative moves, and obviously our index system does not work like that. So it's unclear where exactly those pieces were in cyberspace. But we can fix that in a hacky way by only taking moves that are actually positive in destination. Well, original and destination. So this should stop some buggy behavior. And again, that part is completely my bad because I found that bug later than I posted the shell. So I'm sorry for this extra bit of work. We can just indent that a bit. And before we move on to the next stage, why don't we just test that has fixed some of the inane behavior we were experiencing. Okay. Okay.
It looks like a condition, but it's not.
If I I don't take, will his pawn disappear?
This one's fine, but that does.
No, that's good. You should take back.
No, you should let it run.
I should let it mount? Okay.
I mean, that's a place for bugs.
That is one thing we haven't tested.
Looks like it should have been here, and it actually might break something.
Luckily, it's really easy just to restart games.
Of course, there's a question, do we really want to find bugs?
Hey Brett,
That is another question. Yeah.
can you go, can you go to line 320?
Well, it's function move to.
Oh yeah, it's in the function move to.
Mhm.
There's a weird, maybe I'm just not smart
Yeah,
enough.
wait.
There, right there,
325.
325. There's an AND function in there. Is that a bug or is that? Because I don't know if there's no
You're
like
writing
condition.
move twice to a boolean. So if R and the absolute value is less than 1, so
Yeah.
greater than 1, then you write that.
I think it would
Then
like.
do what?
If
It
the
would
move
first.
twice becomes a bool, it's like 1 or true or false.
I think it is intended.
Oh no, yeah, you're right.
Interesting.
Yeah, you're right. It's just gonna.
Yes.
Alright, cool. Thanks, man.
I was just confused because like there's a condition
Oh yeah,
like
right
in the next
below it.
line, and I thought it was just about. Yes.
Right down the page.
No. It's
I'm just gonna try and let him promote.
my bad.
Okay, good.
Okay, so he should take and go to queen right away. It's still giving us the choice. Yeah, promotion's not quite working.
Promoted my rook.
Wait. Okay, I would have enjoyed seeing that. Okay. So, like Douglas said, it's unclear whether we should be hunting down these bugs right now, but I'm just gonna see if we can crack it real quick.
Yeah, I was like, where did you put it?
Yeah. What's up?
For some reason, line 636 gave me an error when I tried to
Line 626,
636.
36.
I 630. Did I miss something?
I can just,
Wait, I think I'm done. Oh, there were 6 Oh, I think that's
There has been one type of that.
I think that might have been a problem with your self-generated
I didn't change it.
Right, yeah. You just go back up.
idle.
I was comparing 1 and 1.
So when is simulating movement turning on? That's a good question. You scroll down to your simulating movement. Evaluate position. So is evaluate position ever returning in?
Take my stuff. For the one to take its stuff.
Yes, actually. It looks like you never returned the evaluation.
Hopefully that's it.
You guys remember?
Can we have a quick look at Simulate to Move?
Sure. That's
Does castling work?
Castling works on your side, but
As far as they get the computer to pass them.
Yeah, the computer will not pass. If we went back to random. Did you find a problem?
No, I missed updating the position.
Oh, okay.
And then you don't reevaluate after you update the position?
No,
So
no.
you just return the evaluation?
Yes, yeah. Sorry, we can't capture all of it quite yet. Yeah, we only want to evaluate after the first move, and then the rest of it is just undoing what we just looked at.
Undoing, okay.
Yeah.
But, why is it that always like the blacks pawns at the rook moves one step forward? Irrespective of whatever opening you do.
What's your question?
Irrespective of whatever opening white does, the blacks.
Why is it always moving like that?
Why is the rook's pawn always moving?
Right. So that's because we are evaluating one move ahead, but all the moves are completely equal at the start of the game. Like it's still a 0-0 eval for him. So he just sticks with the first move because he never found a better one. So he's always going to make the first available move unless it can recapture. That's intended right now. Yeah. Kind of boring. Okay, so I think we should try and move on rather than fixing this queen promotion bug.
Oh, yeah.
It's frustrating.
I think that's a good idea. It's getting kind of
Yeah, it's
so.
getting kind of late.
Oh, yeah. Could we look at safe moves also?
Sure, yeah.
What is your
So what if here doesn't? What if B1 evaluates to false? What happens then?
So really this check is kind of redundant
Oh, it's
because
redundant. Okay.
we should never be calling it an invalid piece. Like that's only going to happen if we're trying to move a blank square. So this is just trying to catch errors later on in the
Oh, it's
code.
like some sort of assertion.
Yeah, it's an assert in a way. Really though, if it were an assert, it should say something in the else. Like you try to make an invalid move. Which would be a reasonable thing to add.
What happens when your kings are no, mine doesn't end. My king's dead.
Okay, so we should try and move on to the next stage.
Oh, no, I can't.
Even though we have those few bugs. We got an AI that will recapture, which is nice. But it would be nice if he could see further ahead, because he still makes bad decisions. So we can try.
Where are you gonna move?
Just to show you the picture real quick. In case anyone's not familiar with Minimax. We're trying to look further down the game tree and minimize our opponent's answer while maximizing our best move. This is just the general idea of a search tree.
I didn't get it.
Agree. Big problem. Yeah. Okay. Okay. So, the way Minimax works, we want to have an evaluation at the very bottom nodes. So essentially the simulate move calculations that we're doing in computer move right now need to happen on the final layer only. And then from there we're just going to select min and the max all the way up to the merge, right? But we need to make a separate function from computer move and essentially just take our current eval method and put it there. So to get back to it. Right now we're essentially just going to be moving this computer move logic of like finding the best evaluation into a different function so that we can later call that in the Minimax search at the final layer at least. I called this final depth search, but you can think of it in different ways. It's important to include the term because we might end on a state which is White's term, not ours. So I mean, it's exactly the same as just that one depth, right? So we might as well just take this logic in the interest of saving time. So take the logic you wrote for computer move, and we're just going to move that straight into final depth search. Okay. Now this does take a little more logic insofar as we need to be doing a different evaluation, or we need to be selecting things differently insofar as if it's black's turn, we're going to do what we're already doing, but if it's white's turn, we need to do the opposite, which is, the minimizing. Or it's just an intelligent decision from either side. So current evaluation, or no. If black turn, then we're going to use a current logic. Else, it's the same idea, but reversed.
Actually, if you want to avoid like lexicographic thing, we could maybe toss a coin if it's equal.
You mean just making a move randomly?
I mean, so here, like, if essentially we don't have the equal case, right? It's either if it's less, then we.
Yeah.
But if it's equal, we could actually.
Right. Introduce a little bit of
replace
variability into it.
Sometimes.
Yeah. Get some variance. I like that idea. It would at least make the AI a little more fun to play against.
Yeah.
So I think we might as well.
But you need a separate equals case.
As in, yeah. If less than, if equals, then flip a coin, maybe replace.
Yeah.
Will it be common that there's a tie in the evaluation?
I can't hear you.
Will it be common that there's a tie in the evaluation?
Definitely at the start of the game. We were experiencing that a little earlier.
Where is the black turn variable coming from?
So that's something we're going to be using later on in the Minimax search.
Oh,
We
you
needed-
define it as a parameter.
Yeah, it's a parameter. Short answer. I'm just going to add that because it seems like, what is it, yeah. That seems interesting. So we're going to roll the dice here. Right. So if current depth is equal to max depth, then at that point we want to return the final depth search for black turn. So from there we still need to see all possible moves from our current position. So you can do that by, once again, calling generate legal moves. Oh, or actually taking a turn now, which is important. We did that in foresight of Minimax. So if it's black's turn, then we need to try and aim for lowest position evaluation. Whereas if it's white's turn, then we need to go for the max. And I'm just leaving these comments for the sake of clarity. Okay. So we can jump into it. I'm running a little low on time, so I'll try to go fast. Make sure to still ask questions though if you're lost or anything like that. So once again, I chose to start the best tuple at the max possible. And like someone pointed out earlier, you could start with the first move, but you're going to be searching the first move anyway. So I don't think it actually saves you that much. But, you know, it's worth thought. So we can look through every move in our move options, and soon we're going to be using the move simulation technique again. And just a quick word on how to mentally think of the Minimax algorithm. So the way we work with simulating and then redoing moves, if you remember writing the simulate move function, we're going to be enacting the move, calling Minimax a level deeper, and then doing it on the way back. You can kind of think of it as, I guess, the function stack unwinding, right? So you want to slowly undo the moves as you're coming back from your search depth until we return to the original game state. That's just like a high-level view of what we did. But simulate the move, and we're not going to call our old function because that actually called eval and all those extra steps. All we want to do is actually make the move. So we're going to call safe move. Zero, or I guess this fancy new trick. Oh, caught myself. Search deeper, reverse turn, and okay. So once you actually simulate the move, you want to look a level deeper, but from the opposite perspective. So we're just going to swap our parameters. Well, we need to actually catch our result. So we're going to call ourselves with current depth plus 1, so we're actually going deeper. And you want to just change black turn, just so that it oscillates. So these are checks that, these initial 2 checks, just checking that Minimax tuple actually exists. I don't remember what error case that combats, but just in case it was an important one. Once again, we're running a little short on time. There we go. So this will actually update with a better move tuple. And then we actually need to undo the move after recursive call. So this is code that's very similar to the simulate the move function, just the second half really. So you want to move the piece back. And if you captured something, way back here, then we want to set that piece. Just modify the board directly. Piece. It's worth noting that just the way this chess game is implemented, it's not easy to actually go back and forth between the moves. A simpler implementation would be an actual move stack, like I sort of hinted at earlier, or you can just pop and look at the previous move very simply. But yeah, this is the black side, and we need to do just a very similar thing. In fact, yeah, I think we might as well copy paste from the other side. So paste that in the white side, and then we'll make the tweaks. Starting tuple should be black winning by a lot. I think that's actually the only change that needs to be made. But just to be sure. Oh, okay. I forgot to add a return statement, so you definitely need to return something if you are black. Can't get away with not doing it. Yeah. Minimax tuple has the evaluation in the first slot. So that's what we're doing when we're only looking at this first index, comparing the best tuple. So we are carrying the moves back up the stack. Best tuple. Just the same thing there. And I think that actually completes our Minimax function. Any questions?
The return statement that in your code, is that still in the for loop? Can you tell?
Based on the indenting?
Yeah.
Yeah, it shouldn't be. Thank you. Yeah, I also lost that. I can't even see the for loop on my screen anymore. That should be after you loop through all the moves. Okay. Any other questions? Or we can just jump straight to. Okay. So now we can move back to the computer move function. And we're just going to adjust this to actually use the Minimax algorithm just for that. Just to make sure I don't mess something up. Okay. So we don't really want to be using the simulate move function anymore. We can still keep it starting with the first move in the list. But I like the randomness aspect we introduced. So we're actually still going to be looking at every possible move. We still need to look at that. But the difference is we're going to be calling Minimax from every possible position that results from that. So if you're starting to detect repeated code, you are completely right. So once again, we want to enact the move. I wrote looked up on. Enact the move, then do Minimax search, and then undo it on the backside. And you can actually, we want to start at depth 1, but you can actually pick what depth you want it to go to. 3 might actually be a bit ambitious. We'll get to find out how efficient our code is. But yeah, we could even just keep it to depth 1, and then it's essentially doing exactly what we're doing before. But I'm just going to delete this. So now that we have best tuple, I'm going to be using that same theme of if the eval, as in index 0, is better for us than current best eval. I believe we called it best valuation, yeah. Best valuation. Then you want to update it. Best move equals this tuple. Or actually, move, not the leaf node. Best tuple equals just like before, we want to undo the move we just made. So let's see the save move. 1. If there was peace, replace it. Outside of the move for loop, we will have actually found our best move. It should be stored in the best move tuple now. So we can just make that. I think it's best move. Best move 0. Best move 1. Oh, yeah. We already have that. Okay. Remember to still change the T at the end. And once I forgot something in between, we should actually be searching now. First, I'm just going to try it on depth 1. So this should be essentially the same thing we were fighting before, because it's only searching one move ahead. So to capture, maybe it'll still take that pawn. Will it take mine? Okay. Yeah, it seems very similar. Okay. So luckily, I mean, we wrote a lot of code and it still compiles, so it's still a little bit victories, really. So we can try making that depth 2 true. And you'll find if that you mix and match the depths with, you know, like say we pretend we're white, we can get the AI to perform very, very poor moves. So if you really like beating up a computer opponent, it might be a good idea. If you pay attention on depth 2, you can see that there's actually some weights there. By the way, it seems like our random choice did not actually work, because these moves are still very predictable. Yeah, depth 2 is not looking very good at all. I think it's because you might want to change to false. We can try to stick with the odd numbers, 3 true. Because of just how many times we're calling generate moves, this will probably take, a significant amount of time. It's thinking.
Oh, what?
Bold. Very bold. Okay. These choices seem to be very poor. Okay, I mean, at least you need to recapture that time. So I think it's worth just toying with the depths for a second. And you can feel free to experiment with that on your own. One thing I'll say is that, in retrospect, I regret not going for the Minimax approach, because Minimax is actually a little unintuitive for what we're looking for, and I'm pretty sure that some of the meaning was lost along the way. So, I mean, we got him to make some relatively intelligent choices. These He's not very smart, but no. He's trying his best. Okay, I mean, this combination of values seems to have produced an AI that's at least not suicidal, so we can rejoice in the little victories here. So I went with current depth 1, max depth 3, and false, which makes sense because we did just act out black's move right before calling Minimax.
Max depth 10.
Bold. I like your spirit. Okay. So from there, actually, the next improvement is to upgrade our evaluation function so that all the moves aren't considered neutral at the start of the game. Or that's just one way to think of it. I think I might want to just... This next step is actually a lot of code because it's trying to imbue the AI with positional understanding, and that can be a little tedious. So maybe I should just go over let's go over the high level concept. So the idea is the next thing we do is to create arrays for each piece. Like there's an array for pawns, there's an array for bishops, an array for knights, and you rate their position. Like a knight on the side of the board is going to be worth a little bit less than a knight in the center of the board where it has a strong position. Rooks are encouraged to be like on active files, that kind of thing. Pawns are encouraged to promote. Just a lot of positional ideas that are, it's just tedious to write out, really, because you need to have, a 64 size array for every single piece, and you need to flip it when you're looking at black versus white. So it's actually approaching 8 o'clock, and I hope no one was expecting a very strong AI, because we definitely did not manage to do that. But we can talk about some future improvements that we can make if we wanted to make a menacing chess engine. So first of all, bit boards. Part of the reason our AI was so slow is we weren't using the lowest level machine representation of what was going on. So when I say bit boards, what I mean is oftentimes there will be separate 64 index arrays for like white's pawns are all displayed in their own separate bit board, white's bishops, black's bishops. Essentially every kind of piece is stored in a separate bit board, and you can perform very efficient operations for checking what threatens what or what can take what. Essentially, generate moves would be a lot more efficient if we used bit boards. Alpha-beta pruning, which we mentioned earlier, would help out the inefficiency that was very noticeable at any depth past 3, really. So that would be very important. One key thing is Minimax into Negamax. Minimax is intuitive to understand. Like if you look at the graphic, your opponent wants to minimize your score, you want to maximize your score. But I don't know. I think the way we implemented it definitely left a lot to be desired. One more thing, transposition table, which I mentioned a little earlier, where you store positions and you can basically you just have an O1 lookup next time you see the same position in your search. I'm not sure that was really a problem here, but now this quote is meant to be a little facetious because our AI was not very intelligent at all. But perhaps it was still genuine thought. Who knows? Yeah. Dijkstra is a smart guy. Anyway, thanks for coming.